Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 947, most stones removed with same row or column. This is a medium level difficulty graph problem. We're told that we've got a 2D plane and we place n stones at some integer coordinate points. And each coordinate point may have at most one stone. And we're told that a stone can be removed if it shares either the same row or the same column as another stone that has not been removed. And we're given an array of stones, and each stone is represented on a grid with its x and y positions. And we need to return the largest possible number of stones that can be removed. So we need to return the largest number of possible stones that can be removed, and we remove these stones only if it shares the same row or same column as another stone that can be removed, or that has not been removed yet. So it's a bit confusing to understand the way this problem is kind of worded, but let's actually hop into this. So let's actually visualize this grid that we were given. So we're going to say 0, 1, 2, and then we'll do the y-axis as well. And let me actually plot this like this so that we can see. This is actually not that straight. That's a bit better. And now we can actually map where these stones are. So 0, 0. Actually, let me go back to red and let's just get this top one done for my OCD. Okay, so 0, 0 is where we're going to have one of our stones. 0, 1. So 0, 1. X is 0, y is 1. 1, 0. So 1, 0. 1, 2. 1, 2. 2, 1. So 2, 1. And 2, 2. So 2, 2. Okay, so we can remove 2, 2. Why can we remove 2, 2? Because it shares the same row as 2, 1. So so it shares the same row as 2, 1. So we remove 2, 2. We can remove 2, 1 because it shares the same column as 0, 1. We can, well, I've actually done this the opposite way, but it works the same. Remove stone 1, 2 because it shares, so 1, 2 because it shares the same row as 1, 0. So that's true. We can remove stone 1, 0 because it shares the same row as 0, 0. And we can remove the stone 0, 1 because it shares the same row as 0, 0. So we removed 5 stones. We can't remove 0, 0 because the stones that we remove have to be on the same row or the same column as another stone which has not been removed. So we don't remove the 6 stone, we only remove 5 stones and we leave 1 stone. So how can we actually solve this problem without using a grid? Well, this is, like I said earlier, a graph problem. And the way we're going to solve this problem, it's basically hidden in plain sight, but it's a component counting problem. So we need to calculate the number of components which are connected to each other. So in this example, believe it or not, there is only one component. All these stones are connected to each other. So this is a single component. So what does counting components means for getting the number of stones that can be removed? Well, let's think about it. The number of stones, it's going to be the number of stones minus the number of components is going to be equal to the stones that need to be removed. So that's going to be our formula for today. And why does this work? Well, in this example, we should remember that for each component, there's always going to be one stone left, like we had for 0, 0, just in this example. 0, 0 is a remainder, but this is going to happen for every component we come across. There's going to be at least one stone left, which is going to be the stone which allows all the other stones to be removed, but that stone itself cannot be removed. So we're going to get the number of components are going to be the number of stones remaining, and we're going to subtract that from the number of stones which we're given, which is going to give us the number of stones that can be removed. So we're going to exclude removing the stones that can't be removed and only remove the stones that can be removed. So n minus c is going to be equal to the number of stones to be removed. Okay, so now that we've got this, let's actually get coding up. Let's build our adjacency list. So our adjacency list is going to be equal to a default dictionary And actually, let's actually first get the number of stones. It's going to be length of stones. Get the number of stones, just so that we can process this later. Default dictionary of list, and we want to also get the number of rows and columns, so we can map the rows and columns to each other before actually building our adjacency list. It's a bit more complicated compared to doing it normally, but we basically need to map each stone to the row and to each column, and then build our adjacency list from this map. So we're going to say for RC in stones, let's say rows R, and we're going to append R and C. Let's actually append as a tuple. And then we can say columns C.append R and C. So now we've created a map for each stone. We've added it to a row and we've added it to a column. And now we need to build our adjacency list. So we can say for each row and column in stones, for each row and column, we're going to go through all the rows, or we're going to go through all the stones, sorry. And we're going to say as long as this new row and new column, as long as this new row and new column is not equal to the row and column itself, we can append it to our adjacency list. So we're going to say adjacency list rc.append, and append new row and new column. So that's for us in stones. So this is us building our adjacency list. So this is for stone, for rows. In rows R, we don't want to do the stones. We want to go through rows R, and then we want to go for columns C. And then we're going to build our adjacency list like this. So this is our adjacency list built. Fantastic. Now let's actually do breadth first search and count the number of components. Let's do component searching. So component counting. So basically is going to be equal to a set. Component is going to be equal to 0, and we're going to say for each stone. So this gets a bit confusing because we're going to be throwing R's and C's everywhere. But just imagine each R and C as a stone. This is just the X and Y position. So we're going to say for each stone in stones, as long as the row and column is not in visited, so as long as this stone is not in visited, we can now count the component. So we can mark off, we can add component plus equals 1, components plus equals 1, and now we can mark off all connected nodes, all connected stones. That's the word I'm looking for. So let's set our Q equal to a Q, and we're going to pass in row and column, and we want to say visited.add row and column, and we're going to say while Q, the node or the stone, but let's just say node because it's stuck in my brain to use node. Node is going to be equal to Q.pop0, and what we want to do now is get all the neighbors. So we want to do the same. We want to mark off all neighbors. So we want to get new row and new column and we want it to take adjacency list, and we want to pass into our adjacency list the node. So we want to get all the connected stones, and we want to say as long as NR and C is also not in our visited set, we can say visited.add and add NRNC, and then we can also append NRNC. So we can say QE.append NRNC. Okie dokie. And now that we've counted all the stones, or we've counted all the components, I hope this code is all correct. So we've added, so what we're doing here is we are adding our row and column to our visited set, and then we're appending, so we can carry on doing breadth first search and marking off each stone, each component of stones. Okay, that makes sense. So now we've got our formula, which is n minus c. So we're going to say return n minus c, which is the number of components. And I guarantee you there's a pretty high chance that we've made some syntactical errors. Okay, so here we need to make this into a tuple. This is probably not going to be the only error as well. Or I spoke too soon. It looks like the code works and it passes all 69 test cases. So I hope you guys enjoyed this video. I hope it made sense. Definitely recommend rewatching and attempting the problem yourself. It is a bit of a confusing problem, but once you understand that it's a graph problem and it's simply a component counting problem, build out adjacency list takes a bit of code to do that. Once you wrap your head around building the adjacency list, then it's just breadth first search to count the components and then returning the number of stones minus the components. So there's a bit of logic involved. But with that being said, I hope you guys enjoyed this video and I'll catch you in the next one.